Cool. So thank you everyone for coming. My name's Jamie Winsor, and I'm going to give you a talk today about Habitat, specifically building Habitat and building Builder with Habitat. Okay, I'm just going to... So here's some contact information for me. I'm a longtime game developer. I'm also a longtime Chef user. I wrote Burkshelf and Burkflow and Ridley and a bunch of supporting libraries for Chef. I'm also an evangelizer of cookbook patterns and worked on League of Legends, Guild Wars 2, Lord of the Rings Online, and most recently a mobile game called Moonrise. But now I work at Chef. I joined last year to work on an R&D project. Like I had said, I'm a longtime Chef user. I've been using it since 07 or 08 or something like that. And I learned a lot about operations and application automation from Chef. It got me super, super far. But it didn't get me 100% of the way there. I think that Chef is great for infrastructure, but it's just good for applications. It's almost there. About 95% of the way there, but there are little code smells that you'll pick up. And there's a lot of training required to get people going with Chef. I developed Burkshelf and Burkflow to try to help people understand and have a simple path to get somewhere. And through developing those things, I realized a couple of principles that I was chasing after. Specifically, automation needs to live with your application. You can see that because I promoted that you should have your cookbook live with your software and it should share the same version number, and then if you change the software, you rev the version number of the cookbook. And a little bit of a code smell there is like you want to make a change in the cookbook, well now your whole application has to have a version rev, right? So you can feel like a little bit of resistance there. It doesn't really want to be used that way. The other thing that I realized is that you should prefer build failures over runtime failures always. This is really simple, but in Chef, a convergence can happen, and you tested it on your build server. You tested your cookbooks. But for some reason, it fails as soon as the cookbook converges in production, and you're not exactly sure why. That would be a runtime failure. The build failure would be that your cookbook failed its tests, or your software was unable to compile or something like that. And then the last one is that you should prefer choreography over orchestration. Basically, what that means is with an orchestrator, you tell a fleet to do something. You instruct it. And say there's 1,000 machines across 2 different data centers, and half of them fail, a quarter of them fail. You need to handle those cases. And orchestration is basically you trying to wrap another problem and solve it with a giant hammer. Whereas choreography is things working together. You put a bunch of musicians on stage, and they know what song they're supposed to play, but they play off of each other. So if the drummer speeds up, which he's probably going to do, everybody else has to speed up, right? And you can do that with applications. I actually wrote a failed orchestrator, and I'm glad it failed because it was the wrong solution. I really don't believe that I could have gotten it right. A lot of people have tried to create orchestrators to orchestrate our infrastructure, and just not one of them has really done the job for me, including the one I tried to make myself. Some other things that I think are really important to having your automation living with your application is these 4 other principles, which are your application deployment process should be atomic, meaning it's all or nothing. It should be isolated, and you can see that with the emergence of Docker. Docker basically isolates your environment. Your application lives inside Docker and nothing else, right? And it's because if you go onto some random machine and you install a package, like say you upgrade OpenSSL, but it's a application, multi-applications are running on the machine, you don't know what you did to one of them, right? That's not an isolated environment. That's a shared environment. And deployments should also be repeatable and auditable. So if I do the deployment one time, it should always work. And one of the things that you'll notice with cookbooks is a lot of people use like the package resource with no version number. And you don't know what version of that software is going to get it deployed. So technically, you did not have a completely repeatable installation there. And then auditable is what is running on my machines right now. Some of you might have heard of inspec earlier today. And that test suite can run on your machines to tell you when you have an issue. These 4 things we packaged into the R&D project I was talking about called Habitat. Habitat moves those runtime failures that I was talking about into the build time. It also embodies choreography instead of orchestration. Habitat has supervisors that run together and tell each other about what's running. And then the supervisors react to the presence of other supervisors by telling your application about new supervisors and new applications turning on. It also lets you have isolated builds and atomic builds. So any number of versions of glibc can be on the machine with any number of versions of software consuming them. And the same for OpenSSL and any of the other libraries in the Linux toolchain. But I'm not here specifically to talk to you about Habitat. I'm going to assume that you have a basic knowledge of Habitat and you at least saw the 101 or the 201 talk. Today I'm going to talk about Builder, which is what my primary goal was after the initial push of the Habitat supervisor happened. Builder is a software as a service platform to build your packages, basically. It's not finished just yet. New features will be rolling out over the next few months. We don't have an exact time frame yet, but it's both a package repository and a build service. It's open source, and you can run it on your own infrastructure. You don't need to use our public one. This is actually live today. You see it, and it looks like the supermarket for Habitat. The first address is the web client, and the second one is the URL for if you were going to program against our API. So I've had a lot of questions about, like, why am I building another build server, right? There's Travis and there's Jenkins. And we believe that a purpose-built build service built into the community site would allow you to do things like provide public hosting of packages. We needed that anyway. Public builders for those packages. And a history of where those packages came from. And you can look at any time and say, oh, this version of OpenSSL that I use, what was the build output of that? And theoretically, 10 years from now, you should be able to go back and look at whatever the version of OpenSSL was built. I don't know why you'd want to, but you could technically do that. Another thing that, by building our own build server, lets us do is automatic rebuilding of and republishing of your packages when a dependency of yours changes. And for people that aren't familiar, this is a plan file. This is for a component of Builder that I've built. And there's 2 lines there. One is package deps, and then there's the package build deps. Package deps are what we depend on at runtime. So when I say automatic rebuilding of things, I mean that when core OpenSSL gets updated, we will automatically rebuild your software to be linked against that new version of OpenSSL if you want to. If you don't want it to rebuild, then you won't need to. But this is important because Habitat assumes the happy path. You don't need to have this on, but it automatically updates your software for you if it's running and connected to a public depot. So if we find an SSL vulnerability, core is our origin, and we publish a new version of OpenSSL out, automatically your software will know there was an issue, rebuild against the new OpenSSL, publish to the public depot, and then your software that's running, as long as you have auto updating on, will pick up those updates, and you won't even be woken up in the middle of the night, right? Like, if you had inspec set to waking you up if there was a vulnerability of a certain threshold, you won't even see it, most likely. We'd catch it, publish this out, or if it did wake you up, it would be too late. 5 minutes would go by, your software would be rebuilt, and it would already be running on your stack. So I want to talk a little bit about building Builder. And that's basically the premise of this talk, is to educate people about Builder for users and also for people that are potential collaborators, and show how Habitat helped us build Builder. So a little bit of a warning here. It's going to get technical. And I'm going to take a drink of this coffee to get ready for the technical parts of this talk. Great coffee. Okay, if you haven't seen the 101 talk or the 201 talk yet, this might be a little rough. And I'm going to assume some knowledge of Rust. And I know that I asked the room before this if anyone knew Rust, and there wasn't a hand. So feel free to ignore the slides that have Rust on them, and I will just tell you what it says. I hope that this talk helps people as they get more familiar with Rust. And like I said, we'll have a hack day, and I'll be present in trying to help people out and get up to speed. So the first thing you need to know about Builder is that it is a service-oriented design. And it's really important that we built a scalable system here, because the thing that I just mentioned about dependencies automatically rebuilding is like a stampede problem. Everything depends on glibc. And if we change glibc and we update it, every piece of software in that depot that's still active will need to be updated. So there's clever ways that we're solving this, and we're going to go through those. So there's 3 tiers here. One is gateway nodes. Their job is to authenticate you, format your requests into the cluster, and then they send those through router nodes, and their job is to send them to the appropriate service. Service nodes are like session server and the place that stores all your personal information, and the job server. And this is the service layout. Each one of these is written in Rust, except for the databases and maybe the clients. You could write the clients in Rust. On the top, we have gray boxes. Those are the 2 clients that connect into the HTTP gateway. The black lines represent connection paths, so clients connect into the gateway. The HTTP gateway is a RESTful interface. It's one of the edge nodes that performs authorization, authentication, and it also formulates your request for the inner of the cluster. It's also in a public subnet, and everything else is on a private subnet. Or at least that, if you deployed it, I would recommend it to be that way. The gateways connect into the routers, and the routers are fully meshed. So there's 2 connections between them. Those are the only fully meshed nodes, and that's important because those are the only things that can talk to each other. Below that, there are services that connect into the route servers, and they don't know about each other. So a job server can't message a session server directly. It has to message a router and then bounce the message off of it to, so say session wants to talk to job, it sends a message all the way through the router and then to the job server. Then at the bottom we have the databases. The services connect into their databases, and we have a worker pool which connects into the job server to pull off jobs to do the builds. So one of the big questions that we've been getting is why Rust? Go is a really popular language right now. It's great. I'm a big fan of Erlang and Elixir. I programmed with that for a couple years and had a great time. Why Rust? I didn't even know it when I first started. I just knew it was this fringe language that I should maybe look into at some point. But I'm actually in love with this language. It's a systems programming language that is blazingly fast. And it also offers a thing that's unique to systems programming languages, which is memory safety without a virtual machine. And what that means is you cannot have double freeze, use after freeze, dangling pointers. There is no such thing as a memory leak unless you are using unsafe Rust, and we won't talk about unsafe Rust right now. It also has thread safety guarantees and great tooling, which makes it basically a modern C. Completely awesome to work with. So this is the really technical part. I want to educate people in the room about how Builder works and how we process your job, because I want developers to help us build this. So this next bit here is going to be us starting a new build and how a worker picks it up, does the work, and then publishes it to the depot. And there's 10 hops. Each one of these hops represents a place that a message gets handled and then transformed and then sent on to a next node. I'm going to go through how you authenticate and then how you create a new job from a project and then how the worker comes in and picks it off. So the first hop is the client. The client's going to request that a job is done. And they're going to hit the REST gateway, or you're going to use the web client, and it's going to hit the REST gateway as well, because our web client is written in Angular 2, and it's just a client-side MVC JavaScript app that one of my teammates, Nathan Smith, made, and it is really good. I was never a fan of JavaScript, and that guy showed me some really crazy, awesome things that you can do with it. And it's probably one of the best front ends that I've had the pleasure of touching. So the HTTP client's going to send a message to the HTTP gateway. This is the second hop. Like I mentioned, the REST gateway or the HTTP gateway is the public-facing edge node. It performs external authentication to make sure you're okay to do something or identify you. So we do that with OAuth, and right now we do it through GitHub. So basically, you take your personal access token that you generate from GitHub and you put it into an authorization header and say, this is who I am, and it comes through. We transform your request into a NET request, and then we forward that along to the router. After we forward it along, we sit there and we wait for a response. We call these network transactions. So the authorization bit is specified in an authorization header. We rip out the value of that. We put it into something called a protocol message, which is a binary message. And then we're going to forward that along to any route server available. And then the route server is going to forward that request to the appropriate session server, because the session server handles authentication for you. So you can see the path of the request, and at the bottom, we're now on the session server. So I talked about binary protocol that we're speaking, or the network protocol. And we call that BuilderNet, or the BuilderNet protocol. And it's comprised of two components. One is 0MQ sockets, and the other one is Protobuf. Protobuf is a language-agnostic DSL. Basically, that bit at the bottom there represents a struct, and that could be compiled into any language. So when I try to create the protocol messages for Rust, it comes and reads these proto files and would change that representation into Rust code. What's neat about this is any language can talk to any one of the servers that's in the Builder cluster. Like, they're all written in Rust right now, but they don't need to be written in Rust. As long as you can talk Protobuf, which every language has an implementation for it almost. It's not every language, but a lot of languages have an implementation. You can talk to our services. Something that is really powerful about Protobuf is that it also provides backwards compatibility between service versions. So if a new service comes online, we update a service, and it receives a message from an out-of-date server, it will still be able to read and decode that message. And that's really important for the way that we want to operate. We want our service to be choreographed together. I don't want to take an outage because I need to update. I want to do a rolling restart, and I want Habitat to coordinate that for me. I also want to store these in a database at some point, so it's really nice to be able to have that backwards compatibility. The other bit is 0MQ. These are just sockets on steroids. It's not a message bus. It's not ActiveMQ or RabbitMQ. They are literally sockets that have queuing in them, and they're very customizable, super easy to work with. Also, not specific to Rust. Implementation of this exists for many languages. And there's an excellent C library, so if your language doesn't support 0MQ, you could tie into that, but most major languages have it. So these sockets speak Protobuf. Turn Protobuf messages into a binary protocol, and then they get sent through to each and every service. This is the basic envelope for all of our messages. When we talk about network services talking to each other, they always have an envelope wrapping the content, and this is what that is. There's 2 bits here and then the content of the message. So if I was to have an envelope here on the stage, I would have the destination, which is the route information. That's like what the post office would do to know where to send this thing. And then I'd have the message ID, which is like, hey, what kind of thing is this message? That's a hint for decoders and for dispatchers to know how to handle the message. And then there's the serialized message body. So anytime you see another Protobuf message on the screen here, the body is an encoded version of one of those, and this is just the envelope that wraps it. I've also included a path. So if you cloned our source tree, you can find the builder protocol component, and inside there's this protocols directory that contains every protocol. So with the authorization, we basically take that header out, we create a brand new session get, and we jam the token into the token field. So the third hop is the route server. I mentioned that the HTTP client talks to the gateway. The gateway says, I need to do some authentication, and then send it through the route server to the session server. Well, how does the route server know how to get it to the session server? What it does is it reads that envelope information, like the post office has that routing info, like where's the destination, right? So the route info composed of two parts: the protocol, which is what service you're trying to send this message to, and then the second one is the routing hash. And we'll talk about that in a little bit, but that's for sharding. The route server reads the routing information and then it forwards it across to the appropriate service, which brings us to the fourth hop, which is the session server. So the session server is going to receive that message for the route server, and it's going to dispatch that session get message to a handler. What's important here is that developers coming in don't need to worry about this very complex, multi-threaded environment. It feels to you that you're working in something I like to call a single-threaded server, or an STS server. When you get a message into a handler, you can do anything you like with it, but it's basically your space. You don't need to interact with any other threads. It's very easy to work in. So the handler reads the token, looks in the data store for the session. If you have one, it's going to say, here's your session, and if you don't have one, it's going to give you back a net error, and we'll talk about those in a second. That's basically what a session message looks like, and that would be in the session server.proto file. So when we reply, if it's an error, we return this thing called a net error. Net errors are a response to a transaction on a failure case, and they have two parts. One is the error code, and then the other is the error message. The error code is for the user. It's so that way we can do localization, basically. Error code 8 means session timeout. Error code 1 means generic timeout. I just happen to know what a bunch of them are, but any client could then represent it in any language. The next bit is the message. It's confusing because it's called message, but it's not for you. It's actually for the developer. It's composed of three parts. One is a 2-character code for the service. 2 is what operation or function was happening at the time of the failure. And 3 is the case. So for instance, RG-auth1, I know means that we were unable to go talk to the external service to verify that your session was valid. You could also find that out by just grepping the source code, which makes this really easy to debug what happened in this large distributed system. Normally people wouldn't sit up here and tell you about errors in their system and like how to handle them, but I think it's really important because the code base is large and it's service oriented, so there's a lot of pieces that are moving, and knowing how to debug problems is really helpful. But we're going to assume that this was an okay case, so we're sending back a session. So the fifth hop is that the route server receives the transaction reply from the session server, and it sends a response to the appropriate HTTP gateway. This is important because there could be multiple HTTP gateways that the route servers know about, right? And how does the message know how to get back to the appropriate route server? And we'll get to that in a second. So the gateway is going to receive that message, receives the reply, and then it knows which client thread to send it for. Again, no one in this room needs to know how to do that. It automatically does it. The client thread then creates a new project get message from the HTTP parameters that you originally sent when you said I need a new job. And basically a project is associated to every package that you have. So a package could be core nginx, right? In the build service, you'd have build output or the ability to say, I want to build core nginx. So that's the project. And the project is associated to like a GitHub repository, the path to the plan file it's going to build, and some additional information there. Unfortunately, the UI is not ready yet, so I can't show it to you. And it might make more sense later when I can show some UI too. But the project get stuff is specified inside of the Vault protocol file. So we say what project we want, and what we're going to do is route that message all the way through to the Vault server. We'll talk about the Vault server in a second, but this is a good time to stop and explain how the messages are actually getting the right place. Because I mentioned that we sharded our data. For anyone in the room that's not familiar with sharding, basically that means that there's X amount of buckets that are identical, but they contain different information in them. So in this room, if there was 100 people here, and we had 100 shards, theoretically, one of us would be in every single bucket if we were able to distribute evenly across the shards. What it also does for us is if a shard goes down, we don't have a full outage. And this also allows us to scale out easily by moving shards to additional machines. So here, what we have is 2 routing servers, and they're connected to 4 vault servers. And those 4 vault servers have these numbers in the bottom. They represent shards. So shard 0 through 127, we have 128 shards. We pre-shard our data 128 times. So vault server 4 over here, if that goes down, only 32 shards go down, which means that only a percentage of the room would have an issue, and they would only have an issue if they were working with the vault server. The vault servers then connect into the databases, which have those shards as well. So the databases have the data sharding. So Builder is service-oriented and sharded. Like I mentioned about outages, one of the reasons that we did this was to prevent full outages of our system. We also did it to distribute out. But if a service goes down, only have a partial outage for that service. So if the job server goes down, it's okay. You can still log in and download packages and everything's fine, but you can't make new jobs. If a shard goes down, you only get a partial outage of that service for a subset of users. So the more machines we have running our shards, up to, we'll say 128, because I pre-sharded 128 times, if one node goes down, only 1/128th of the population experiences an issue with that service. This also allows us to add new machines by rebalancing those shards. So I add a new machine, and then the shard migrates on over to it. So now that we know what sharding is, I can kind of explain what the hash is. The hash determines the destination of the shard. There's a point where we have a message, those protocol messages, and there's one field on every message that's important. It's called the route key. And the route key is able to be defined in Rust by specifying a function that returns a value. I know that no one in the room knows Rust, but basically what this says is that a message, a protocol message, has a function that then returns something or nothing, and if it returns something, it's a value to then hash and put into the hash value of the envelope. What this allows us to do then is mod that hash against the amount of shards that we have, and then deterministically route your message to the appropriate place. This is the implementation of the trait that I just showed. The top is the project get message, which would get compiled into Rust code, and then this is me implementing the routable trait for project get. And you'll see that what I'm returning in this function that I've defined is an InstaID that I'm creating from the ID of the message. Which brings us to our next important bit, which is how all of our entities are cataloged. They all use something called an InstaID. An InstaID is a 64-bit integer, but it's not opaque. It has 3 parts of it in there that you can pull out. One of them is the create time, which is exactly what time it was created since an epoch, which allows us to create messages for entities for 75 years or so before you run out of IDs that we can give out. I'll be dead by then, so it's okay. You guys, that's your problem in 75 years. Sequence ID is automatically generated by the database, which allows us to create 1,024 messages every second or so. And then the next bit is the shard. This was inspired by Instagram engineering. It's slightly modified from theirs. So what this allows us to do is every time we create a new thing on a database, we know exactly what shard it came from, because the data of where it came from is hidden inside that identifier. And the identifiers are guaranteed to be unique because they're sequentially increasing over time. I can also take every job that's ever been created or every entity in the system and tell you what time it was done at, just by looking at the ID. So there's a hell of a lot of data here in just 64 bits. This is the implementation in Rust. I'm not going to leave this up there very long, but basically what it shows you is that the first 32 bits is the time, the next 13 bits is the incrementing ID, and the last 10 bits is the shard ID, and that's how we generate one. So let's get back to things. What we were just talking about was project get. We were getting a project on the HTTP gateway through the Vault server to then be able to ask the job server, hey, I want to build a job based on this project, and that project is Core Engine X, let's say. So the Vault server receives the message from the router. It then dispatches it to a project get handler, just like we discussed before in the session server. It reads the project from the database, and it replies to an HTTP gateway through the route server. So the message comes back to the HTTP gateway. Important here is, what is that Vault server? Why was the project there? Basically, the Vault server is persistent storage for origins, projects, any shared entities, and anything not specific to your exact account. Your account stuff lives on session, and then every other thing that exists in our system lives in a distributed entity store called the Vault server, which is backed by Redis, which brings us to how we persist Protobuf messages into the database. What's really neat is we have that backwards compatibility, and Redis is a key value store, right? So if a new version of the software comes out and it pulls an entity out of that database, because we stored it in a Protobuf message, we are able to translate it into the newest version and then restore it into the database, and things should be just fine. We can persist the Protobuf messages directly into the database with a trait that's just like that routable trait that I showed, which basically just needs you to define two functions, which are a primary key and how to set that primary key. And this is the implementation of it. Just as simple as the last one. The top is the project that you'd have, and then the bottom is saying that the ID is the primary key, and that's all that says. So this is hop 8 of 10. We're almost there. Is everyone still with me here? No? No one's napping yet? Okay. So we receive a reply from the route server, and we create a new job spec from the session in the project. A job spec is saying, like, I want a new job. It's from this project. And then we're going to message that through the route server to the job server, just like every other service. And that's what a job spec looks like. It has an owner ID, who started the job, and the second bit is the project that the job originated from. Job server receives that message. It dispatches the job spec to a job create handler, creates a job, persists that to the database, and the database happens to also be a queue for us, which is OS specific. So there's a Linux queue and a Windows queue, right? And the job server stores it in the whole job history that you have, the state of the job. Active jobs, like I said, are placed in an OS specific queue, and then job create success or failure eventually gets sent back to the client through the route server through to the HTTP gateway. So now the HTTP gateway says, okay, I got my reply, it was successful, we created your job. Now we're going to serialize your job into JSON, and we're going to send you a 200 OK with the JSON representation of the job. And again, we use a trait to say this protocol message looks like this in JSON. So every time you've seen an implementation of a trait, it's saying this is how we route it, this is how it persists in the database, and now this is how we represent it in JSON. So the JSON response is simple. It's just the ID and the state. So the jobs are there. Your job's done. You were told the job is created, but it needs to get picked up by a worker. So there's a pool of workers that are running connected into the job servers, and they're OS specific. So there's 4 workers here, 2 are Linux, 2 are Windows, and there are any number of workers connected to any number of job servers at a time. They're OS specific, like I said. Builds are done within a studio on the worker. This is huge. Fletcher Nichols on my team, he spent a lot of work on this thing called the studio. I'm not sure if anyone here has sat through the talks yet, but I'm getting some nods. It is amazing. When he first made this thing, I didn't know what it was for. I know that he's a really smart guy, and I just trusted him. And I was like, Fletcher, take the wheel on this one. And eventually, when I got to the part where the worker needed to go build the software, my mind was blown. I had to do nothing, simply nothing. It shells out to the Habitat binary we already have and says, Hab Studio, build this. And then we have a container that runs the whole job that you asked for, and in an isolated environment from everything else on the system, which allows us to have safely run jobs. So like you can't give me something bad that will destroy my worker node. Nothing will be left over between nodes. So if one member of the audience runs a job and then another one runs it and then I run something, I don't have any of your artifacts or anything like that or any of your secrets. It's a fully contained environment that gets spawned every single time a worker picks up a new job. So the next bit is that Habitat Builder is actually self-hosted. So when I said that I used Habitat to build Builder, this is what I mean. Habitat supervises all the Builder processes. And the supervisor watches the public depot, which is itself, to wait for package updates of itself. Builder builds itself and sends its package to itself, and then it automatically updates when a build is published to itself because it was watching itself. And this totally works, and I can't believe it. This is pretty much the part where it all came together, and I just did not expect it to happen, and I had to go for a walk right after it. It was like, oh, my job is done here. So this is what the source tree looks like of one of the Habitat components. We have the plan.sh file, which is the entry point. We have a config directory there. And you'll notice inside the config directory that there's no default toml. The default toml is the thing that is the translation layer. It's like a template in Chef on how you take things that the gossip layer is telling you and turn them into configuration for your node. The reason there's no toml is because Builder uses the native configuration that Habitat Supervisor just dumps out anyway. And this is some of that. You can see that there's some generic configuration up there. And then there's down here at the bottom, bind routers members. That's actually dynamic. That was found and written to our config file because of something that we call binds, where this service found more routers and will automatically configure itself on the presence of new routers. And by using the native configuration file, it made my plan template even simpler because I didn't need to have any sort of translation layer. This is not required, but it's really neat. If you're building services with Habitat in mind, you don't need to, your plan gets even simpler. Who in the room has heard of the director? Cool, that's more than yesterday. Excellent. So the director is a thing that supervises supervisors. And this is important for Builder because Builder has a lot of components. And what we want to do is have one thing run and then monitor every supervisor that's on the node supervising our software. So this is a systemd config of the director, which starts from a configuration file. This is the configuration that it's starting and passing to the director, which is very simple. It's toml again. The important bits here are that start, those parameters are what you would pass in the command line. And you can see that I'm binding a database, Redis, and then an environment router, and I'm binding router and have build router from an environment as well. So this says that I'm going to look for a database Redis in this environment. And above it, I happen to also be starting a Redis database in that environment. So the last slide I showed you binds, routers, members. This is how that gets populated, using binds. Bind is basically service discovery. The last bit that I want to talk about that Habitat really helped me out with is shard allocation. So this infrastructure that I just described to you, if you've ever seen a talk that I gave a year or two ago, not at ChefConf, but at somewhere else, about Moonrise, the game I was working on, it should look very familiar because this is a video game backend architecture that I've just purposed for a build server. It's a generic distributed system, right? But one of the big problems that I had when I was working on Moonrise was allocating those shards. Turning on the initial environment was a pain. You had to handcraft some environment JSON or for your environment, put it in the Chef server, run everything, pull it from the Chef server, and then if you made any changes, you needed to go edit the central Chef server again, and then run Chef and hope that, and basically build all the logic into the application that shards need to be rebalanced. The way that I was able to solve this is using the topology flag inside of Habitat by having a master router be elected through this flag. Basically what happens is a master router turns on and it's going to expect n number of nodes of a service to come online and ask it for shard assignments. So the master router turns on and says, I expect 4 session servers. So it will pre-shard, it will take the 128 shards, divide them up 4 times, and hand them out to servers as they come in. What this allows us to do is, all you need to do to add a new server is add a new server with the topology flag set to leader. It'll join the ring. You increment the number of servers you expect. As that new guy comes in, the master router says to the other nodes, I need some of those shards back. So we take a partial outage, and it hands them off to the new server. And I didn't need to do any of the leader election because Habitat did it for me. And there's one more thing that I want to talk about, which is bring your own worker. I talked about gateways, the REST gateway. And I also talked about how your packages could be auto-built if one of your dependencies that you depend on changed. Well, what's hard about that is we only have a certain number of public workers available. And if I change OpenSSL for core, everyone's package is going to update. And another thing is, like, if there's no public workers and you have a build that must go out, well, you need a fast lane. And One of the things that we're going to be providing at some point is a gateway for you to connect your own workers to. You can make your own workers, as I described the protocol. It doesn't matter what language you use. You do not need to use Rust, or you can use our worker, connect in, authenticate through a gateway for workers, and then you can have a fast lane for your builds. So bring your own worker is basically any machine that you want to connect into the public cluster. You don't need to set up or maintain the cluster. You just connect the workers in, and basically how we're going to be able to handle auto rebuilding the entire world is by telling you that you need to bring your own workers, else the public workers will never be available. We have a Habitat Hack Day tomorrow. It's 10 a.m. to 3 p.m. And I'll be there. I'm going to be trying to help people with Rust and the code base. I'd love to see anyone come that's interested in either Builder or Habitat or Rust. And that's it. Thank you very much, everyone, for coming.